Now we're going to take a little detour and we'll start talking about algorithms. We'll start talking about simulations. And when we say simulation, it's a process of generating a random draw from some distribution. So in statistics and in Bayesian statistics, simulation is the process of generating a random draw. From a distribution. And the distribution can be identified in two different ways. It can be defined through the cumulative distribution function or probability density function. And you remember they are related to each other, of course. So we're going to use capital F for the CDFs, and we're going to use small f for the PDFs. So the f of x is basically probability that a random variable x takes the value smaller or equal than small x, and we can calculate this value using the density function. So it's density of x, and we integrate x out, and x goes from minus infinity, and let's say this is a random variable that defined everywhere in real line, minus infinity to small x. Okay. So we'll see how to generate those draws, how to do it in univariate case and multivariate cases, and we'll see applications later on. We'll use it in Markov chain Monte Carlo algorithms and particle filtering algorithms. So we'll start with a few simple facts. So let's say we have a random variable capital Y, and the cumulative distribution function of small y is the probability that a random variable y is less or equal than y. And let's say y is the transformation of another random variable x. Then it's just the probability that g of x is less or equal than y. And if g function is monotone, then we can write density function of cumulative function of y using the density function of x. It's just an integral over the density function, and the boundary depends on this value g of x on the transformation function. So this relationship allows us to generate random draws. We'll see how it works in the next slide. So the first theorem is, let's say that x has density function small f of x, and y is the transformation, y equal g of x, and g is a monotone function. Then the density function of y equals to the density function of g inverse of y times the derivative of the g inverse with respect to y. And there is a multivariate version of it. Instead of the absolute value of inverse of the derivative of the inverse, we'll just have a Jacobian function there. And so you can start applying this relationship, and you can calculate a PDF function, for example, when you have a continuous random variable and you want to calculate distribution over x squared of it. So a specific example, when x is standard normal, what will be the density function of the square of the standard normal? Well, we know the answer. This is actually a chi-squared distribution, but you can calculate it using this relationship. And this is probably the most important one, and this is the relationship between the uniform and the target distribution. So let's say we have capital U, which is just a uniform random variable defined on 0, 1. And then we're going to have any continuous distribution function. We're going to call it capital F. Then random variable x equal to inverse of f applied to U has distribution function f. So let's think of the consequence of that. The consequence of this is the following. If you know this, if F inverse is known, then you can generate a sample from this distribution given by F. This is the cumulative distribution function. Basically, it's a two-step approach. You generate U from uniform, and this is relatively easy. And then if you take F inverse of U, we're going to call it X, then there's going to be a draw from distribution given by this density function, capital F. And this can be shown using two simple facts. So the first fact is that if you have a uniform random variable defined on 0, 1, then cumulative distribution function of it is just U itself. So here's your U. This is your cumulative distribution function for this uniform U. And so cumulative distribution defined in 0, 1, and U itself defined in 0, 1. So it's just going to be a linear function like that. And so this is one fact, and then we just use it to calculate the distribution function for the x. So distribution of x, probability x less than or equal than small x, is we replace x with f inverse of u, and then we apply f on both of the sides. So on the left hand side we have u, and then f of x on the right hand side. And again, since u is uniform here, then we know that the distribution function for uniform is just the value of the x itself. So in this case it's f of x. And so if we take x as inverse of the u, f inverse of the u, then we get a random draw from the target distribution that we are looking for. So that's one of the ways to generate random draws from any density function. The only thing is that you have to be able to invert the distribution function to make it work. And the same applies to multivariate cases. So let's say we have a multivariate distribution bivariate. In this example, we have two random variables, x and y, and we have a density function for x and y. And then we have a transform. So x and y gets transformed to u and v. And then the problem of calculating the density function for u and v is calculated using the Jacobian. Jacobian is just the matrix of first derivatives, and then you take determinant. So this is a determinant of this matrix of first derivatives. And so here's how the change of variables works. You have the distribution over u and v is just a distribution over x and y. And then you have this h1 uv, h2 uv. So h1 and h2 are the inverse transforms. And then you have this Jacobian here. And one nice little trick here is that instead of calculating derivative with respect to u and v, you actually can calculate derivative with respect to x and y. So you don't really have to invert the transformation functions. And instead of calculating derivative with respect to u and v, you can just take 1 over Jacobian, where Jacobian is calculated derivatives with respect to x and y. And here are a few inequalities that we also will use some of them later on. So the Markov inequality. So the probability that g of x greater equal than c is less or equal than expectation of g of x divided by c. And in this case, g has to be a positive function or non-negative function. Chebyshev says that if you take the distance between x and mu, the average, and you calculate the probability of this absolute value of this distance to be greater or equal than c, then this is small in invariance of x divided by c squared. And Jensen inequality says that expectation of phi, and phi in this case is a concave function, is less or equal than phi of the expectation. And Cauchy-Schwarz says that correlation of x and y less or equal than 1. And we will just list here those special distributions that are typically used in the Bayesian analysis. Just a quick reminder here, Bernoulli binomial. So you remember Bernoulli is just a coin flip. And binomial is generalization of it. You have n coin flips. So Bernoulli just has one parameter p, probability of success or probability of heads. And in n coin flips, you also have p, probability of observing heads in each of those coin tosses. And binomial models the number distribution over number of successful outcomes k. Poisson distribution, we're going to be talking about it. Usually models some arrival processes, so it's discrete also, and models some arrival processes. Used a lot in the queuing theory, also used in the spatial temporal modeling when you try to model some discrete processes in space. Things like traffic accidents or crime rates would be modeled using the Poisson distribution, or actually negative binomial is another distribution used for these cases. Normal distribution, okay, is of course the most commonly used distribution, and one of the large applications come from a central limit theorem. You remember that central limit theorem tells us that averages from any distribution will asymptotically follow normal distribution. And then you have another set of continuous distributions, gamma, beta distributions, and multinomial distribution is simply you have a finite set of possible outcomes, and you assign probabilities to them. And then bivariate normal, so you have two variables, and V-share distribution. We'll see it's a distribution that is used as prior for covariance function in Bayesian analysis. So it's just a quick list, a quick reminder of those distributions. If you forgot about them, you can just open Wikipedia and look at those distributions. And before we switch to the next topic, I want to do a quick graphical explanation that hopefully going to be intuitive of how this CDF inverse works. So remember, the CDF inverse allows us to sample from any distribution. So you sample from a uniform 0, 1, and then you apply CDF inverse to it, and then it gives you X, which is a random draw from distribution given by this probability function F. So graphically how this works, so let's say that we have normal 0, 1, and we want to generate a sample from this normal 0, 1, and the CDF for the normal 0, 1, so it's gonna the normal random variable defined everywhere on the real line, and CDF is going to be equal to 1/2 at 0, because you have 50% chance to be on the right of 0, 50% to be on the left, and it's actually symmetric S curve, which asymptotically goes to 1 when it goes to infinity, and goes to 0 when it goes to negative infinity. And so if you think about this, what uniform draw gives you, it gives you a number between 0, 1 on this axis here. So, and let's say you pick number here, and what you would do, you would basically go here and you find the corresponding value of X. And so this value of X will be the corresponding random draw from this normal 0, 1. So what we have here, we have this X, and this is CDF of X, and X is normal 0, 1. And as you can see here, most of the time, so let's say I take this interval, let's say 0 0.7, 0.3. So in this interval, most of the times, so the values from this interval will fall into this interval here. So whenever I pick any number between 0, 3 and 0.7, I get the corresponding X value which is going to be around 0. So most of my uniform draws will correspond to the values of x at around 0, which makes sense. We have a normal density function. It's centered at x, and it has a peak at the x, and that's how we generate those draws.